Welcome back to another deep dive here at the Rooster Podlog.
Always a pleasure to be back.
Today we're taking a look at something that's pretty fundamental
Yeah,
to a lot of what makes technology, fast and efficient,
it really is.
and that's cache eviction. Our listeners have flagged this as something that's, kind of a bit mysterious and you want to get a better understanding of. And so our mission is to, really unpack why cache eviction is so essential and how the different strategies for managing it work.
Absolutely.
Think of it as like taking a look at the cleanup crew that
Mm-hmm.
keeps your computer's fast lane running smoothly.
Yeah, that's a great analogy. So to give everyone a really clear picture, let's kind of start with the why. Cache memory, it's that incredibly fast storage that's designed to hold the data that your computer thinks you're going to need next. And it just makes, access times lightning fast.
Right.
But the catch is the super speedy storage is also really limited in size.
Yeah, it can't hold everything.
Exactly. It can't hold everything. So what happens when it fills up? Well, we need a system.
Right. A set of rules.
Exactly. A set of rules or strategies to decide which pieces of data we should remove to make room for new and potentially more important information.
Yeah.
And this whole process, this kind of digital decluttering, is what we call cache eviction.
And it's crucial, right? I mean, without it, that fast lane you were talking about, it just becomes a bottleneck.
It does.
It's like imagine a tiny VIP room,
Mm-hmm.
but then it's suddenly crammed with, every single person who's ever been important.
Mm-hmm.
It would quickly lose that VIP status, wouldn't it?
Oh, absolutely. Yeah.
So similarly, if the cache couldn't evict old or less used data,
Yeah.
it would just be filled with outdated information.
Mm-hmm.
And then your computer would have to constantly go back to the main memory, which is much slower.
Right.
And that completely defeats the purpose of even having a cache in the first place.
Yeah.
It really makes me think of that famous computer science quote. The one from Phil Carlton where he says, there are only two hard things in computer science, cache invalidation and naming things.
Oh, yeah. Classic.
So today we're tackling that first challenge, that challenge of cache invalidation.
Absolutely, and it's a big one. It's really key to understanding how our systems work efficiently. So to make this a little easier to digest, we're going to break down 7 different strategies that systems use to decide what gets evicted from the cache. And to make these concepts a bit more memorable,
Okay.
and maybe have a little fun along the way, we'll be using an analogy based on, Churn's trade wars
Okay.
to really illustrate the core logic of each strategy.
Love it.
Yeah, so for each strategy, we'll talk about, when it's a great tool to use and when it might not be a best choice. We'll also ground this in some real-world data engineering examples to show you how these concepts actually play out in the systems that power our digital lives.
Yeah, so by the end of this deep dive, you'll have a solid grasp on these essential concepts
Yeah,
and their practical implications.
definitely.
Okay.
So let's dive in.
All right, let's get started with our first strategy, least recently used, or as it's commonly called, LRU. So what's the basic idea behind this approach?
Okay, so LRU, it's all about evicting the item that hasn't been accessed for the longest amount of time.
Right.
And this is based on the principle of temporal locality, which is, the idea that data that has been used recently is more likely to be used again soon. So if something hasn't been touched in a while, well, LRU says it's probably a safe bet to evict it.
Makes sense. So how does our Trump trade war analogy help us visualize this LRU thing in action?
Okay, so let's imagine that Trump needs to, kind of redirect his attention and his resources to a brand new trade dispute. So following the LRU principle, he might choose to put on hold or even completely abandon trade talks with countries that he hasn't engaged with in a while.
Okay.
Maybe a smaller trading partner like Estonia, he's going to shift his focus to those more recent and active trade relationships.
Okay.
Perhaps those with China. So the less recently active negotiation gets put on the back burner
Right.
to make room for the current priorities.
Okay, so it's all about what's been on his desk the most recently.
Exactly, yeah.
So in the world of computing then, when is LRU the best strategy to use?
So LRU really shines in workloads that have strong temporal locality. Like think about when you're browsing the web. The websites that you visited in the last few minutes are way more likely to be revisited than a page you looked at a month ago.
Right.
So LRU leverages that. It's also super effective for managing user session data in web applications because users tend to interact with the same data during their session.
Right.
Most interactive applications benefit from LRU.
Okay, so what about those times when it's not the best choice? When does LRU fall short?
Okay, so LRU can face some challenges with scanning workloads. Imagine a database system that's performing a full scan of a large table. As it reads through each row,
Mm-hmm.
those recently read rows might actually push out frequently used but less recently accessed index pages
Oh,
from the cache, even though those index pages are going to be needed again soon.
right.
The sequential nature of the scan disrupts that temporal locality that LRU relies on. Also, if you have an application where important data is accessed infrequently, LRU might prematurely evict it.
Just because it hasn't been used in a while.
Exactly, yeah.
So it's not a perfect system. It's really context dependent.
Exactly.
So can you give us some real-world examples where we would see this being used, like real systems where LRU is the go-to strategy?
Sure, you'll find LRU in all sorts of systems. So in a customer data platform, for instance, LRU could manage the cache of customer profiles.
Okay,
And this is used for real-time personalization. So the profiles that haven't been viewed or updated recently,
right.
those are the ones that get evicted
Okay.
to make space for the profiles of the customers who are actively engaging.
So it's always keeping the most relevant stuff.
Yeah. Another example is API gateways.
Okay.
They use LRU to cache responses for frequently accessed API endpoints,
Right.
ensuring that those common requests are served quickly from the cache and those less popular ones can be evicted.
Yeah, it's all about speed.
It is, and even your operating system uses LRU-like algorithms
Oh, wow.
to manage its page cache,
Interesting.
deciding which blocks of data from your hard drive to keep in RAM.
Okay, so LRU is everywhere.
Pretty much, yeah.
All right, let's move on to our second strategy, least frequently used, or LFU. How does this one approach things differently?
Okay, so LFU, instead of focusing on when an item was last accessed, it looks at the total number of times an item has been accessed.
Okay,
So the strategy here is to evict the item that has been accessed the fewest number of times overall.
all right.
So the assumption is that items that have been accessed frequently in the past are likely to remain popular and should be kept in the cache.
Okay, so how does this Trump trade war analogy work with LFU?
Okay, so imagine Trump allocating his, limited negotiation resources based on the volume of trade with different countries.
Yeah.
Using an LFU, he'd dedicate most of his attention and his diplomatic efforts to the countries with the highest trade volumes, places like China or the European Union,
Okay,
because historically those relationships have been the most active.
right.
He might be quicker to abandon or deprioritize those countries that have minimal trade volume with the U.S.
Makes sense.
So it's all about that frequency of interaction.
Interesting. So in data engineering, when is this LFU the better choice?
LFU is really good for situations where you have a relatively stable distribution of popularity.
Okay.
So if you've got certain pieces of data that are consistently accessed more than others over long periods of time,
Mm-hmm.
LFU can make sure those popular items stay in the cache.
Right.
So content delivery networks are a great example of this. Certain assets like the homepage of a really popular website
Right.
or a frequently downloaded file,
Yeah.
those are going to be accessed a lot, and LFU helps keep them available at the edge. It's also great for caching reference data that gets looked up frequently.
Okay, so it's good for that stuff that's always in demand.
Exactly.
But what are the downsides? When should we maybe avoid using LFU?
Okay, so LFU can struggle when those popularity patterns change over time. So something that was once really popular might become less so,
Mm-hmm.
but because it had a high access count in the past, it might stay in the cache longer than it should,
Right.
taking up valuable space.
Okay.
Also, LFU has this issue called the cold start problem.
Okay.
When a new item is added to the cache, its access count is initially 0.
Right.
So it might get evicted early on,
Even if it becomes popular?
even if it's going to become super popular later on. Yeah.
Interesting. So can you give us some real-world data engineering examples of where we would see LFU used?
Sure. So a recommendation engine might use LFU to cache information about the most popular products,
Okay.
because those are the ones that are likely to be requested by a lot of users.
Makes sense.
Another example is in a data warehouse environment. LFU can be used to cache frequently accessed dimension tables.
Okay.
These tables are used in a lot of queries,
Right.
and they tend to have stable access patterns.
So they're a good fit for LFU.
They are.
Okay, let's move on to a strategy that seems a little counterintuitive at first. Most recently used, or MRU. Why would you ever want to evict the thing that was just accessed?
It does seem a bit backwards at first glance.
It does.
But the idea behind MRU is that in some very specific access patterns,
Okay.
once an item has been used, it's actually less likely to be needed again immediately,
Okay.
and the older data might be more important.
Interesting. All right, so how does our Trump trade war analogy work with this MRU thing?
Okay, so imagine Trump just finished a big trade deal with, let's say, China. Following the MRU strategy, he might then immediately shift his focus away from China,
Okay.
the relationship that he just used. He's going to start focusing on new trade disputes or maybe escalate existing ones with other countries.
Right.
So the assumption is that the China deal is done for now, and his immediate priority is elsewhere. The most recent engagement is the one he's least concerned with at that moment.
Interesting. That's quite a specific scenario.
It is.
So in computing, when would this backwards approach actually make sense?
So MRU can be useful in situations where you're dealing with sequential access,
Okay.
especially with large data sets. Like, imagine you're doing a scan of a huge file.
Mm-hmm.
Once you've processed a chunk of data, you're moving on to the next one, and you probably don't need that previous chunk immediately.
Right.
So evicting that most recently used block makes space for the next one in the sequence.
Okay.
It can also be good for applications that cycle through large data sets,
Okay.
processing each item just once and then moving on.
All right. So when is MRU a bad idea? When should we definitely avoid it?
If you have any kind of workload where there's temporal locality,
Okay.
where recent access suggests a higher probability of future access, yeah.
MRU is a bad choice. You'd constantly be getting rid of the stuff you need most.
Exactly, yeah.
So are there any real-world examples of this being used?
So some time series analysis pipelines might use MRU.
Okay.
If you're processing a stream of data and you need to keep a cache of historical data,
Mm-hmm.
you might evict the most recently processed data points because your focus shifts to the new incoming data.
Right.
Similarly, some anomaly detection systems that keep a baseline of recent behavior.
Mm-hmm.
Once a data point has been analyzed, it might be evicted using MRU as the system focuses on the newest data.
Okay, so it has its niche uses.
It does.
Right, let's move on to a strategy that I think is a little more intuitive. Time to live, or TTL. What's the idea here?
So with TTL, we're focusing on the age of the data in the cache.
Okay.
So each item gets assigned an expiration time, a time to live.
Mm-hmm.
And once that time is up, the item is automatically removed from the cache. It doesn't matter how often it's been used recently.
So how does this play out with the Trump trade war analogy?
So imagine Trump imposing tariffs, but with sunset clauses.
Okay.
So he announces a tariff on some imported goods for, let's say, 90 days. After those 90 days, that tariff automatically expires.
Okay.
It doesn't matter what's happening with the trade negotiations or how much those goods are being talked about.
Okay, that's a good analogy. So when is TTL the best strategy to use?
TTL is perfect for time-sensitive data. Things that lose their accuracy or relevance after a certain time.
Okay.
Stuff like stock prices, weather forecasts,
Right.
maybe session tokens that should expire for security reasons.
Makes sense. But when is relying only on TTL not the best approach?
So TTL doesn't consider how often data is actually being used. So something could be accessed constantly but still get evicted just because its TTL expired,
Right.
even though it would be useful to keep it. On the other hand, rarely used data could just sit there,
Taking up space.
yeah, wasting space until its TTL expires. So if the data's validity isn't really time-dependent, TTL alone might not be enough.
So can you give us some data engineering examples of where TTL is commonly used?
Sure. So in financial data caching,
Mm-hmm.
where prices change so rapidly,
Yeah.
cached quotes need very short TTLs. You'll also see it in Internet of Things monitoring platforms.
Okay.
Sensor readings might be cached,
Hmm.
but with TTLs based on how fresh the data needs to be.
Okay.
CDNs often use TTL to manage how long assets are served from edge locations.
Right.
And you can even implement TTL policies at a very granular level,
Okay.
setting different expiration times for different data types.
Wow, so it's very flexible.
It is.
Okay, let's talk about a very straightforward strategy. First in, first out, or FIFO. This sounds like just a basic queue.
It is. FIFO evicts items from the cache in the exact order that they were added.
Right.
So the oldest item in the cache is the first one to be removed.
Okay.
It doesn't matter how often it's been used.
So back to Trump and trade wars. How does this one work?
So imagine Trump addressing trade disputes purely based on when they started.
Okay.
So if he's got a lot on his plate, he's going to resolve the oldest one first,
Mhm.
even if newer, more urgent disputes have come up.
First come, first serve.
Exactly.
So in computing, when would this FIFO approach be a good choice?
FIFO is a decent choice for sequential access patterns.
Okay.
So like when you're processing a stream of data or working with log files,
Right.
as new data comes in,
Yeah.
oldest data might not be needed anymore.
So it's about keeping the cache updated.
Yeah. FIFO is also good when you need a really simple implementation
Okay.
and you don't want the overhead of tracking access times.
So when would FIFO not be the best choice?
So if your access patterns aren't sequential,
Okay.
and if getting a high cache hit rate is important,
Right.
FIFO isn't a good option. Because it doesn't pay attention to how often things are used, you might end up evicting something important just because it was added to the cache early on.
Yeah, you could lose valuable stuff.
Exactly.
So what are some data engineering examples where you would see FIFO used?
So in a system that's processing streaming log data,
Okay.
FIFO can be used to store those recent log entries. And then as new logs come in, the oldest ones get evicted to make room.
Okay.
You could also use it for a social media feed to always show the most recent posts.
Okay. Always keeping it current.
Exactly.
All right, let's talk about an eviction strategy that almost seems like it's based on pure chance. Random replacement, or RR.
Yeah, this one is pretty much what it sounds like.
Just randomly picking something to evict.
Pretty much. RR just selects a random item from the cache and evicts it.
Right.
No consideration of how recently or how often it was accessed.
Okay, so back to Trump. How does this work?
Imagine Trump needing to free up some of his time, and he
Oh.
decides which trade disputes to drop by literally picking names out of a hat.
Really?
Yeah, so he might just suddenly end a trade disagreement with, let's say, Vietnam,
Okay.
not because of any strategy, but
Yeah.
just because it was randomly selected.
That seems so inefficient.
It can be.
So when would you ever use this random replacement?
So you might consider RR when the cost of using a more complex eviction strategy is just too high, especially in systems where every microsecond matters.
Right.
It can also be useful when the access patterns are totally random,
Okay.
so there's no reliable information to use for a better decision.
So in those cases, just picking something randomly is better than nothing.
Sometimes, yeah, the simplicity can outweigh the potential for not getting the best hit rates.
Okay, so when is random replacement a bad idea?
When there's any kind of pattern to how data is being accessed,
Right.
random replacement isn't a good idea. It doesn't learn anything from how the data is used.
Right.
So you're just as likely to evict something you need as something you don't.
Yeah, it's a gamble.
It is.
So are there any systems out there that actually use random replacement?
You might see it in some really simple caching systems within larger distributed systems,
Okay.
where keeping track of usage statistics across a ton of different nodes is just too expensive.
Right.
It can also be a fallback
Okay.
if other addiction information gets messed up somehow.
Interesting.
Yeah, and in some really high-speed data pipelines,
Okay.
where the decision of what to evict needs to happen super fast, random replacement is the fastest option.
Okay, so it has its very specific uses.
It does.
Okay, finally, let's talk about a more sophisticated approach, two-tiered caching.
Yeah, this is where things get a little more strategic.
Okay, so how did this one work?
With two-tiered caching, you're basically splitting your cache into two levels.
Okay.
You have a smaller, faster hot tier for the data that gets accessed a lot, and then a larger cold tier for less frequently accessed data.
Okay.
And the idea is to make sure you get the most out of that fast memory
Right.
while still having lots of overall cache capacity.
Okay, so how does the Trump analogy work for this one?
All right, so imagine Trump has two lists for trade negotiations.
Okay.
There's the critical list with major trading partners like China, the EU, Canada.
Mm-hmm.
Those get constant attention. That's like the hot tier.
Right.
And then there's the secondary list for other trading relationships.
Okay.
That are only addressed when there's time. This is the cold tier.
Right.
So if Trump needs to free up some bandwidth, he's going to look at that cold list first before even thinking about touching the hot list.
Right, so he's got his priorities straight.
Exactly.
So in data engineering, when is this two-tiered caching really useful?
It's great when you've got a clear difference between frequently accessed data
Okay.
and less frequently accessed data.
Mm-hmm.
It lets you use your fastest memory for the stuff that matters most for performance.
Right.
It's also good when different types of data have different needs in terms of how long they need to be kept around or how quickly they need to be accessed.
Okay.
You see this a lot in systems that handle both high-speed transactions and less frequent but important analytical queries.
Okay, so when is this two-tiered approach maybe not the best option?
If your data access is pretty uniform without a clear hot and cold distinction,
Right.
then managing those two tiers might not be worth it.
Okay.
Deciding which tier to put something in and when to move it around can get complicated.
Right, it adds overhead.
Exactly.
Can you give us some real-world examples of two-tiered caching in action?
Sure. So a business intelligence platform might use a two-tiered cache.
Okay.
The hot tier could be fast in-memory storage for frequently accessed dashboards and reports,
Right.
while less frequently used data lives in a larger, maybe disk-based cold tier.
Okay.
E-commerce sites also use this. Best-selling product data.
The stuff that gets viewed a lot.
Yeah, the stuff that gets viewed and bought all the time that might be kept in the hot tier,
Right.
while less popular items are in the colder tier.
Okay.
This ensures quick access to the most important product info,
Mm-hmm.
while still having plenty of cache space for the entire catalog.
So it's all about optimizing for speed and efficiency.
Exactly.
Okay, so let's step back for a second and think about what all of this means for our listeners out there. Understanding cache eviction isn't just some abstract computer science concept.
Mm-hmm.
It really affects how fast and responsive all sorts of applications are, from the apps on your phone to these massive data processing systems.
Right.
Managing that cache data well is essential. And as we've seen, there's no one-size-fits-all solution. Choosing the right eviction strategy really depends on how the data is being used in each situation.
Absolutely. We've gone through 7 different approaches today,
Yeah.
from that really simple FIFO
Right.
to the totally random RR to those more usage-focused ones like LRU and LFU
Yeah.
and then TTO based on time.
Right.
And finally, that more complex 2-tiered caching.
And hopefully all those Trump trade war analogies help to make things a bit more memorable.
I hope so. Yeah, it's always good to make these things relatable.
Yeah, and the real-world examples showed how these concepts actually play out in the systems that we all use every day.
Right.
So at the end of the day, choosing the best cache eviction strategy is all about finding that sweet spot. You want to use those limited fast resources as effectively as possible.
Yeah.
So that the data you're most likely to need is ready to go.
It's all about making sure that the right data is available at the right time.
Right. Minimizing those delays or making everything run smoothly. It's this constant balancing act
Mm-hmm.
between holding on to the data that's important
Right.
and making room for what's coming next.
Exactly.
So it makes me wonder, as we keep generating more and more data at faster and faster speeds,
Yeah.
how well are these traditional cache eviction strategies going to hold up in the future?
That's a great question.
Are we going to need to come up with new, even smarter strategies?
It's definitely something to think about. Maybe even AI-driven approaches could come into play.
Yeah,
It's an exciting area of research.
it is. It's going to be interesting to see how things evolve.
Definitely.
Well, thanks for taking this deep dive with us today.
It's been a pleasure.
Always great to have you on.
Thank you.
Until next time.
See you then.